Today I'm going to talk about dissociation of gas products, which is one of the high temperature effects that's induced at very high speeds behind strong bow shocks. The importance of them is that it changes the properties of the gas. You're going from a multi-atomic molecule to a monatomic particle, if it's dissociation, say, of oxygen. And the process of dissociation takes energy out of a flow, which cools the gas down and affects the density, which is a very important parameter for determining the forces on a hypersonic vehicle. So, in order to analyse this, we need to know at least two things. One is how fast will the dissociation take place, so we have to develop some sort of a model for that. And also, how much does the density change due to the fact that it's dissociating. And today I'll talk about the first one, developing a chemical kinetic model that enables us to understand these flows. Not only understand them conceptually, but to mathematically include the effects of dissociation on the analysis of a high-speed shock layer. There's a good starting point for this given by the Lighthill-Freeman model developed in the 60s, which is applicable only to what we call binary reactions, where each reaction takes place by the collision of two particles, which is proportional approximately to density squared. But for these reactions, rate of reaction is only proportional to the concentration of two participants. If we consider, for instance, recombination reactions, you're looking at three particles colliding at one time, and it's a different process. And this is applicable for use in oxygen and nitrogen systems, such as we have in air, and it's made more convenient by the fact that the areas where oxygen and nitrogen dissociates are separated in flight speed. Oxygen has virtually finished dissociating before we start having the similar effects in nitrogen. So in this figure we can see a shock wave, which is represented as a discontinuity, across which the temperature increases very fast. Now, the temperature increases over a few mean-free paths. You don't really need many collisions between particles to increase the translational temperature up to a very high value. Associated with that high temperature, of course, is a new state of chemistry where the gas wants to dissociate it. However, that doesn't happen so fast because it takes tens of thousands of collisions between particles to get what we call an equilibrium state of dissociation. So if we were to plot, for instance, the concentration of O particles, it would be virtually zero before a shock. After the shock, gas gets very hot, it's way out of equilibrium, so you start driving a process of dissociation. And if you have enough length scale, a large enough model, eventually it will asymptote to equilibrium values. This might be, for instance, the concentration of atomic oxygen. Okay, at the same time as you're building up oxygen atoms, you're losing oxygen molecules, of course, because that's where they come from. So your concentration of oxygen, O2, is steady before the shock, and it will gradually drop. So this is the concentration of O2. And so from looking from here onwards, that might be considered the equilibrium. Region, and over here before that it's a non-equilibrium region. So what's going to be of most importance to us? Well, this non-equilibrium region, it doesn't last forever, but sometimes actually you never reach equilibrium. If you're flying at very high altitude, for instance, and if your space vehicle isn't too big, you actually don't have enough physical time for the gas to reach equilibrium. So the model we're going to look at today will be this stuff over just after the shock. So it's close to the shock, low densities where this reaction process hasn't gone anywhere near completion. Okay, and associated with this process is a change in density. Obviously, as you go through the shock, we know from shockwave theory that density has to jump up by some value. Now, after the shock, because the reaction's starting to take place, you get a gradual increase in density. So this is like Rho over here. It's this process coupling rate of change of reaction, formation of dissociated species, and increase in density associated with a drop in temperature, which we have to understand. This can be predicted relatively accurately with computational fluid dynamics, or CFD these days, but I'm going to give you a simple analytical technique which enables you to solve simple flow situations and get some physical understanding of what's actually happening to the gas due to these processes. Well, this reaction is the mechanism whereby diatomic molecules are split up. Well, they don't just split up unless something happens. If they don't collide with anything, they're perfectly happy to sit there at their condition. So they've got to collide with another particle to split up. These are what we call M's. That's what we call a third body. But the third bodies aren't taking any chemical part in the reaction, but they're there to absorb and provide energy. So the rate of this reaction is proportional to the concentrations of both A2s and M's. So you can see is proportional to a density squared term. So we can formulate a reaction rate in terms of the rate of change of A, atomic species, is equal to some coefficient, which we don't know yet, times the concentration of both of them. That's what drives our forward reaction, which is the main process taking place in the early region immediately after a shockwave. But of course, there's another mechanism for change, which is these particles on the right-hand side. They could, if they wanted, all three come back together and recombine, form the molecular species again, and indeed that does happen. It's happening all the time. So we need to know how fast it's happening, and we have a similar procedure for doing this. So rate coefficient times now the concentration of atomic A squared times the concentration of third bodies. And we have the A squared, of course, because two atoms have to combine for it to happen. If you just have an atom combining with a third body, it's not going to react. So now we need to have a way of categorizing how much dissociation has taken place. And we like to do that by what we call the fraction of the mass fraction of gas that's been dissociated, which we tend to call the alpha. So at any point in time you have a certain amount of dissociated oxygen, say, and the alpha is the mass fraction of oxygen in any forms, which is in the dissociated form. So it's easily expressed by this equation you see here. We can define our densities and molecular concentrations. I'm using these square brackets to designate moles per unit volume. We can formulate the equations you see below in terms of alpha, the amount of dissociation that's taken place. We can rewrite our expression for dissociation in terms of our alpha functions, as you see in the equations shown below. Similarly, we can do the same thing for the reverse reaction rates, and we get an expression as you see here. The net reaction rate is the sum of both the forwards and the reverse reactions. If you actually ever get to equilibrium, forwards and reverse reactions are equal and opposite, so we can establish this condition down here as to what happens at equilibrium. This is also, incidentally, a very useful procedure for calculating the reverse reaction rates, if you know the forward reaction rates, and you know your equilibrium coefficients from chemistry. But we're not going to use that in this course. So if we inspect this equation here, you can see the terms on the right are due to the reverse reactions, the terms on the left are due to the forward reactions. So remember, we're looking immediately past the shock wave, where for a start we're beginning with a value of alpha as 0. So if alpha is small, alpha squared you can see will be negligible. Plus we're typically looking at high altitude flight, so rho itself is 0. So really the only important term in this equation before alpha becomes significantly big is going to be the left-hand one. In other words, a contribution from dissociation. So for the rest of this analysis, we're going to ignore the bit on the right-hand term, or the term on the right-hand side, and we'll consider just the forward reaction rates. Remember, when we do this, we're not going to model anything correctly if we have enough length scale that we get towards equilibrium concentrations, because they're dependent on a balance between forward and backward flows. And any time when dissociation gets too big, but reverse reaction rates become important, that will be not correctly modelled too. So we're restricting ourselves to the regions very close to the shock where it's a non-equilibrium flow dominated by dissociation, not recombination, which actually is quite a large part of the flow field of many flight vehicles. Okay, well, let's start having a look at the forward reaction rates. To react, molecules have to bump into other molecules. But actually it's not just enough to bump into any old molecule. They've got to have enough energy to dissociate it. So these molecules, they're glued together very well with some sort of molecular glue. It takes a lot of energy to separate them. So only the particles which are going fast enough when they bump into another third body will dissociate. And we can come up with a theory to predict what these reaction rates will be. In other words, to find how many of the particles, when they have a collision, will be going fast enough to start a reaction by looking at the Maxwell-Boltzmann distribution of energy levels, a very useful formulation that's developed in the 19th century and still very useful today. It tells us what's the statistical distribution of high energy particles for a given mean particle temperature, or yes. This is the result here of that equation plotted against a velocity squared term, and here it's like a number density. The fraction of, you take a given energy range, this tells you the fraction of them which are going to be in that particular value. So supposing you've got these lines here on the right, maybe everything above this point is going to be going fast enough to dissociate. What we're going to do is integrate this curve and find out how many particles are going to be in a suitable state to dissociate. Well, we don't do it too precisely. We're doing a thing which is more like dimensional analysis. We're getting a reaction rate is proportional to something. So doing this, we can work out that our reaction rate coefficient is as given by here, this exponential term. Now that looks very similar to the Arrhenius relationship, and in fact it is a variation of that. As many things happen in science, we don't really understand it first. We do lots of experiment, plot everything we can think of on different axes, and eventually you find a trend, and then you do the theoretical analysis that predicts the trend. And then in the end we pretend that we knew what was going on all along. So that's roughly what's happened here. We're using a variation of the Arrhenius formula for reaction rates. It's a very useful and versatile formulation. Now if you look at the characteristics in here, the properties, you've got this thing here, theta over T. This theta is a characteristic or representative temperature for the gas we're looking at, and actually these typically have very large numbers. It's like nearly 60,000 degrees for oxygen and 113,000 degrees for nitrogen. What this means actually is that reaction rates are not that big. These are small numbers in that exponential term, and that's why we need to have a lot of collisions between molecules to get any sort of completion of our reaction. Okay, so substituting this stuff back into our equation for how fast it's actually dissociating, where we're including the concentration of molecular species and the third bodies, we come up with this formulation here. Now, the coefficient which is contained in the brackets here, that's normally known as the pre-exponential coefficient. It's actually very difficult to calculate it exactly, so we use approximations. And in fact, many different workers have widely different numbers to take in this because it's not really yet an exact science, this chemical kinetic stuff. But so that can simplify down to a form of the equation where all that's replaced by a constant times t to the minus n. And there's great discrepancy between the numbers people use. Typically, you choose a number that suits the data you have at that particular temperature range, and it's not necessarily going to work at other temperature ranges. So the trick is to try and use the best parameters for the temperature range you're expecting. Okay, we can now rewrite our forward reaction rate in a much simpler way. It's just two terms from the Arrhenius, the pre-exponential temperature dependency and the exponential one, and the simple coupling with density and how much dissociation has taken place already. Intuitively, you'd think once a lot of dissociation has taken place, there are fewer molecules left to dissociate, so the reaction rate's got to slow down. Well, that's true. You can see that through the 1 minus alpha here term. And initially alpha is 0, so it's going off full bore, and that will slow down as more and more reaction takes place. Okay, so if we inspect this term, which is dominated by two components, one on the left here is the density and state of dissociation that's taken place. The other is the temperature. So I mentioned that we don't really know some of these coefficients all that well, so there's a lot of benefit still in doing experiments to try and measure the flow field in a hypersonic reacting situation, and for that we want to use wind tunnels or shock tunnels. So it's important to come up with a rule whereby we can do a scaled test in a wind tunnel and apply the results to flight, and inspection of the terms enables us to do this. The total amount of dissociation you get will be equal to the rate of dissociation, which is the alpha by t term here, and we know that scales with density, that was in there. It'll also depend on the total amount of time that's available. You can integrate it numerically, but it's good to have hand-waving rules to enable us to do experiments. So the product of these two will give us the amount of conversion that takes place. If we do an experiment, we want to make sure we get the same amount of reaction in the laboratory as we do in flight. So this fellow's scaling with density. The one on the right scales with a time. Well, the time it takes to fly past something is a length divided by a velocity. If we're trying to simulate hypersonic flight, we've really got to get the velocity right. So we can take velocity out of of our equation here. So really what we're worrying about is density and length scale. So if you build a scale model, you want to match the product of Rho and L. It's called Rho-L scaling, and it's a wonderful law. It enables us to do non-equilibrium testing in a small-scaled situation. Spuriously, this also gets a number of other scaling parameters right at the same time. It gets your Reynolds number correct. And if your Reynolds number is correct, that means your boundary layer thicknesses are going to be scaled correctly. So it's a very useful scaling law. Okay, so there are a number of limitations to this analysis, obviously. So you have to remember that we can only use this approach when we're looking at regions where reverse reactions are negligible, which is close to the shock. If we ever gets towards equilibrium, it's not going to be right, because if we're doing, say, a scale test at 10 times atmospheric density, the increased pressure in the laboratory will suppress dissociation, because that's scaling with a rho cubed term, and we won't have the correct gas composition, so remember that. But it is very useful for looking at the non-equilibrium regions that dominate the shock layers of re-entry bodies. So I'll finish there with an example of some work we did with our colleagues, whereby we were looking at entry into Titan. Titan's an interesting gas, which is a mixture of nitrogen and methane, which dissociates heavily going through the shockwave. So there's some simulations done by my colleague Peter Noffo from NASA Langley, whereby we looked at a flight experiment, modelling a flight scale on the left, and we postulated a 100-to-1 scale test model to be done in the laboratory, whereby we would conserve this product of Rho and L. So for this small model, we used a gas density 100 times flight, and you can see from the contour plots here, very good agreement was given. So all the approximations we made in this analysis are really not affecting, to a large scale, they're not really affecting the macroscopic flow field that flies around the vehicle.